just what happens is, to overcome the repulsion, yes, an energy is being used. And then further, the electron will be accepted to the shell. Effective nuclear charge is increasing means the nucleus and the electrons will be very tightly bound with each other. What will be the oxidation state of lithium in this particular compound? It will be +1. And for hydrogen, it will be -1. Hello everyone, this is Ambli Unnikrishnan from the Department of Chemistry, Vidhyaashram Pre-University College, the Temple of Excellence, Mysore. So in last class, we discussed about the nomenclature of elements with atomic number more than 100, right? And then we discussed about metals, non-metals and metalloids and their properties, and noble gases and trends in physical properties, wherein we studied about atomic radius and its trends in the periodic table, then ionic radius and ionization enthalpy. So in this session, we will be studying about electron gain enthalpy and its trends in the periodic table, then electronegativity, periodic trends in chemical properties, and then anomalous properties of second period elements, and finally periodic trends and chemical reactivity. Right, so let's begin with the first topic, that is electron gain enthalpy. Electron gain enthalpy. So what it is? It is the energy released when an electron is added to an isolated gaseous atom so as to convert it into a negative ion. So what is electron gain enthalpy? Electron gain enthalpy. Right, from the name itself, when an electron is gained or when an electron is being added to an isolated gaseous atom, a certain amount of energy is being released. That energy or that enthalpy is called as electron gain enthalpy. Right. So let's take the example of chlorine atom, and an electron is accepted by it and forms a Cl- ion. Right. So when this process is happening, an amount of energy or enthalpy is released. Yes, chlorine is accepting an electron or it is gaining an electron and forming Cl- ion. So the energy released at this process is called as electron gain enthalpy. I hope it is clear. Now electron gain enthalpy, negative values it will show for exothermic reactions, and electron gain enthalpy will be positive for endothermic reactions. Now what is this? So what you have to remember is electron gain enthalpy will be having always a negative value. When the reaction that is taking place is an exothermic reaction, right, the electron gain enthalpy value will be negative. Yes, energy will be released, right? So energy is lost from the system. So what happens? The electron gain enthalpy will be negative. Generally, the electron gain enthalpy will be negative. But if the reaction that is happening, if it is endothermic, yes, endothermic means the system is accepting energy, right? That means if we are giving atom an energy so that an electron is being accepted, right? So in such reactions, when the reaction is happening is endothermic, the electron gain enthalpy will be positive, right? So I hope that is clear. Now electron gain enthalpy becomes more negative along the period, and it becomes less negative as we go down the group. Now what about electron gain enthalpy? The trend of it along the period and across the group we are seeing. Okay, so electron gain enthalpy becomes more negative along the period. So what do we know about the trend along the period? We know that the size of the atom keeps on decreasing, right? The periodic trend is that the atomic size along the period will keep on decreasing. Right. So we know that towards the end of the period, the nucleus and the outermost electron will be very close to each other, right? The atomic size is very less towards the right of the periodic table. As we move from left to right, the size decreases. We already know that. So now the attraction between the nucleus and the electron will be very, very strong. That is, they are very close to each other. So what is electron gain enthalpy? That means it is the energy released when an electron is accepted, right? So easily an electron can be accepted when we move from left to right. So what happens as we move from left to right, that is along the period, yes, more and more the negative value will keep on increasing. I hope it is clear. Yes. Now moving on to, it becomes less as we go down the group. So as we go down the group, what is happening? We know that the size increases because number of shells is increasing. So what happens? The atomic size increases as we move down the group. So how it is related to electron gain enthalpy? Yes, as we are moving down the group, the atomic size increases. So is it easy to accept an electron? No, right? Yes, as we move down the group, the size keeps on increasing, right? So electron gain enthalpy means it is the energy released when an electron is being added onto the shell, right? So what happens? It is not easy to accept an electron. So in this case, a particular amount of energy is to be given to the atom so that it accepts the electron, right? So what happens? When we move down the group, the negative value will keep on increasing. Right? So that is, it becomes less negative as we move down the group. So I hope it is clear. Now, there is an exceptional case that you have to be very clear about. So the electron gain enthalpy of oxygen and fluorine is less than sulfur and chlorine. Now what is this? Just now we studied that as we move down the group, the electron gain enthalpy has to decrease, right? Negative value becomes less when we move down the group. So we know that from the periodic table, oxygen, under that comes sulfur, and fluorine, under that comes chlorine. Yes, from the periodic table itself, you can see, right? Yes, oxygen is here and sulfur is here, and fluorine is here and chlorine is here. So actually, what did we study now? When we move down the group, the electron gain enthalpy should decrease. But so what it was experimentally found that oxygen is having less electron gain enthalpy than sulfur. It should decrease. That means sulfur must be having less electron gain enthalpy value. That is less negative value. But oxygen is having less negative value. So why is this? Right. So let's take the electronic configuration of oxygen. It is 1s2, 2s2 and 2p4. Right. Yes. So in the p orbital, yes, we know that there are 3 p orbitals, 1, 2, 3 and 4, right? So already 4 electrons are there. So according to electron gain enthalpy, one more electron is to be added here. Yes, one more electron is to be added. So what is happening here? Already 4 electrons are there. So one more electron, if it is being added, the electrons will experience a repulsion, right? The incoming electron will experience a repulsion. So first what happens is, to overcome the repulsion, yes, an energy is being used. And then further, the electron will be accepted to the shell. Hence, the electron gain enthalpy of oxygen will be less because, yes, some amount of energy is required to remove or overcome the repulsion between the electrons, and then the electron will be added. Yes, so in the same case will be fluorine and chlorine. You can see fluorine is here and chlorine is here. So chlorine is supposed to have less electron gain enthalpy value, less negative value, but fluorine is actually having less negative value. This is because the same case. First, the repulsion should be overcome. So some amount of energy is to be given there, right, to overcome the repulsion, and then the electron is being accepted. So the negative value will be less. So I hope it is clear. The exception is also clear for you. So that is about electron gain enthalpy. So moving on to the next one, that is electronegativity. Now what is electronegativity? It is the ability of atom in a chemical compound to attract shared pair of electrons towards itself. So let's take an example and understand. Yes. Let's take the example of hydrogen fluoride, HF. Okay, so in this particular compound, as fluorine is more electronegative atom, okay, compared to hydrogen, fluorine is a more electronegative atom. So what happens is, this shared pair of electrons, we know that hydrogen contributes 1 electron and fluorine wants 1 electron, right? So basically there is the sharing of electrons between them. Yes, so what happens is, this shared pair of electrons will be a little more attracted towards the fluorine because it is more electronegative. So that is about electronegativity. It is the ability of an atom in a chemical compound to attract the shared pair of electrons towards itself. So this shared pair of electron is being attracted towards fluorine based on the electronegativity difference. In this case, as fluorine is more electronegative, it is attracted towards fluorine. Clear? Now, electronegativity increases across the period as the atomic size decreases and the nuclear force of attraction increases. Now, the trend in electronegativity across the period we are saying. So, across the period we know that the atomic size keeps on decreasing. So, that means the effective nuclear charge is increasing, right? So, effective nuclear charge is increasing means the nucleus and the electrons will be very tightly bound with each other. That means, yes, the strength is more or the attractive force is more there. Hence, the electronegativity will also be more, right? So, when we move from left to right along a period, what happens? Yes, the electronegativity increases. Clear? Now, electronegativity decreases down the group as the atomic size increases and the effective nuclear charge increases. We know that as we move down the group, the atomic size increases. Right. So, from the nucleus to the outermost shell, the attraction will be very, very less as we move down the group. Right. So, hence the electronegativity will be also less because now the attraction between the nucleus and the electron is very less and they are very loosely bound to the nucleus. So, the strength at which it can attract the shared pair of electrons will become less and less as we move down the group. So, this is about electronegativity. I hope it is clear. Now, let's summarize the whole of the physical properties, the trends of it in periodic table that we have studied till now. Okay, so as you can see, let's begin with electron gain enthalpy. We studied about electron gain enthalpy in this session, right? So, electron gain enthalpy, as you can see, across the period, yes, across the period, it increases, right? So, if across the period it is increasing, that means down the group it will be decreasing, right? So, as you can see here, it is shown in this direction. That means it is increasing in this direction means it is decreasing in this direction. Clear? So, electron gain enthalpy increases along the period and decreases down the group. Yes. Now, ionization enthalpy. Yes. What about ionization enthalpy? Even that increases along the period and decreases down the group. Clear? Now, moving on to electronegativity. Even we studied electronegativity in this session, right? So, electronegativity increases along the period and decreases down the group. So, it is showing in the up direction because it is increasing from down to top. So, that basically means it is decreasing down the group. Clear? Now, atomic radius. Yes, we know that when we move down the group, the atomic radius or the atomic size increases, right? So, it increases down the group, right? And it decreases along the period. Shown in this direction means from here to here the size will increase. That means from left to right the size will increase. Clear? Now, so what about metallic character and non-metallic character? Even this we discussed in last session, right? So what did we study? Metallic character increases down the group, right? If it is increasing down the group along the period, what will happen? Yes, along the period it will decrease, right? So that is what is shown here. From right to left, the metallic character is increasing. That means from left to right, the metallic character is decreasing. Clear? And what about non-metallic character? Along the group it is increasing and down the group it is decreasing. Yes, so I hope the whole of the physical properties are clear for you, right? Now moving on to the periodic trends in chemical properties. Yes, still here we discuss about the trends in physical properties, right? Now we are going on to study about chemical properties. So what is first one we are going to study about is oxidation state. Now what is oxidation state? It is a charge acquired by an atom on basis of electronegative consideration of other atoms in the molecule. So let us consider lithium hydride. So in this case, yes, as hydrogen is more electronegative, we will be having a -1 charge and lithium will be having +1 charge. So this charge on top of it, right, based on the electronegativity difference, the charge acquired by the atoms is called as oxidation state, right? So what will be the oxidation state of lithium in this particular compound? It will be +1 and for hydrogen it will be -1, right? Let's take the example of sodium chloride. Right? So, in this case, sodium will be having a +1 charge and chlorine will be having a -1 charge. So, what will be the oxidation state of sodium? It will be +1 and oxidation state of chlorine will be -1. So what you have to remember is oxidation states can be +1, +2, right? Any values it can obtain. It can be positive as well as negative integer values. Yes, so I hope that is clear. Now, the valency of representative elements is usually equal to the number of electrons in the outermost orbitals, or 8 minus the number of outermost electrons in the orbital. Yes, so firstly, it was named as valency, but nowadays valency is represented as oxidation state. So how you can calculate the valency? It is either equal to the number of electrons in the outermost shell, or it will be 8 minus the number of electrons which is present in the outermost shell. So let us see that in our periodic table, right? So let's take the first group elements. Right, in the first group elements, we know that the outermost shell will be having the same number of valence electrons, that is 1. Yes, so the first group elements are highly electropositive. That means they have high tendency to remove one electron from its outermost shell so that it obtains or it attains octet. Right? Yes. So what happens? The oxidation state of the first group elements will be +1 because it is ready to lose one electron. So what does that mean? It is ready to lose one electron, right? So that it attains octet. Hence, the oxidation state or the valency will be +1. The oxidation state will be +1. Right? Now moving on to the second group. Yes, we know that the outermost shell will be having 2 electrons, right? Yes. Let's take the example of beryllium itself. We know that the atomic number is 4, right? So, electronic configuration is 1s2, 2s2, right? Yes. So, to attain stability or to attain the duplet, what do they want to do? They will release these 2 electrons. So, the oxidation state will be +2 in this case. Now, that is about S block elements. Now, let's move on to P block elements. For boron, this family, for the boron family, that is group 13, what will be the oxidation state? So, let's take the electronic configuration of boron. It is 1s2, 2s2, 2p1. Right? Yes. So, in the outermost shell, how many electrons are there? There are 3 electrons. So, the valence electrons is 3. So, how do we calculate valency or oxidation state? It is either equal to the number of valence electrons or 8 minus the valence electrons. Right. So, we know that in this, the outermost shell is having 3 electrons. So, we know that to attain octet, it needs 8 electrons, right? So, to attain octet, either it can release these 3 electrons, lose these 3 electrons, or gain 5 electrons, right? So, what is easy for them? To remove these 3 electrons or to lose these 3 electrons, right? Hence, it will be +3, right? Plus means it is losing these electrons, right? And if it is gaining electrons, negative charge will be there, right? So, in the case of carbon family, that is group number 14, right? So, what is happening there? The outermost shell will be having 4 electrons, right? So, this can be +4. Now, coming to nitrogen family, that is group 13, 14, 15, right? So, let's take the example of nitrogen itself. It is 1s2, 2s2 and 2p3, right? So, how many electrons? Valence electrons are there. It is 3 plus 2, 5 valence electrons are there, right? Is it easy for group 15 elements to gain 3 electrons or to lose 5 electrons? It is easy for them to gain 3 electrons so that they will attain octet, right? So, the oxidation state here will be -3, right? Now, coming on to oxygen family. What will be the oxidation state? It will be easy for them to gain 2 electrons, right? So, it will be -2. And coming to fluorine, fluorine, that is the halogen family. Yes, fluorine, chlorine, bromine, iodine, the halogen family. To them, only 1 electron is required so that they attain their stability. So, hence the oxidation state will be -1. So, I hope the trend in oxidation state is clear for you. It is +1, +2 for the S block elements, and for the P block elements, as you can see, it is +3, +4, -3, -2 and -1. Yes, so I hope you are okay with or you understood the difference between the plus sign and minus sign. So, this is about the oxidation state. So, we discussed about S block and P block elements. Now, what about the D block elements? Yes, they are having variable oxidation state, not just one oxidation state. They are having variable number of oxidation states. So let's consider manganese itself. It is having oxidation states which are varying from +2 to +7. So these many values are there. So hence D block elements are having variable number of oxidation states. So I hope this is clear. Now moving on to the next part, that is anomalous properties of second period elements. Yes, the second period elements show some anomalous behavior. Yes, usually how it's supposed to be according to the periodic table, they are showing certain variations. Yes, certain anomalies in their properties. So let's see. Lithium beryllium forms covalent compounds unlike others which form ionic compounds. Yes, so the S block elements generally they are supposed to form ionic compounds. So the exception is lithium and beryllium, which belongs to the second period, right? So as you can see here, it belongs to the second period, that is lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon. We are talking about the second period, right? So why is this anomalous behavior? It is due to, the anomalous behavior is due to the small size, large charge to radius ratio and high electronegativity of these elements. Right. So anomalous behavior is due to small size. We know that as we move down the group, the size will increase, and as we move along the period, the size will keep on decreasing. So you can imagine it is on the top of the periodic table, means lithium, beryllium will be having very, very small size. Only 2 shells are present there, right? 1s and 2s. Right. So they are having very small size. So that means one is due to the small size, they are showing anomalous behavior, and large charge to radius ratio, that is another reason, and high electronegativity of these elements. Right. So what exactly are the properties which shows this anomalies, you will be studying in the upcoming chapters, right? And then the behavior of lithium and beryllium is similar to that of magnesium and aluminium. That is also one not usual thing that is happening in the periodic table. So as you can see here, the properties of lithium which is present in the second period is kind of similar to the properties of magnesium which is present in the third period. You can see here, lithium is present here and magnesium is here, right? And beryllium shows properties which is similar to aluminium. Clear? Yes. So from boron, it has similar properties to that of silicon, and carbon is having similar properties to that of phosphorus. So as you can see, there is a diagonal relationship between them. So this is called as diagonal relationship. Yes. Why is this called diagonal relationship? See, lithium is present here, or diagonally magnesium is present there in the third period. So these two are having some similar properties. Yes, they have similar behaviors. That is, behavior of lithium and beryllium is similar to that of magnesium and aluminium. So second period and third period elements are showing certain similar properties. So what are these exact properties you will be studying in another chapter. So I hope this is clear. That is the anomalous properties of second period elements, and I hope you are clear with the diagonal relationship also. So why exactly they are showing this anomalous behavior? It is due to the small size, large charge to radius ratio and high electronegativity of these elements. Clear? Now moving on to the periodic trends and chemical reactivity. We are studying about the chemical reactivity here. Okay. Now, the atomic and ionic radius decrease in period from left to right. We know that when we move from left to right across a period, the atomic size keeps on decreasing. Right. So, as a consequence of that, what happens? Ionization enthalpy increase and electron gain enthalpy becomes more negative. Right. Because the atomic size is decreasing along the period, we know that ionization enthalpy is increasing because it is now very difficult to remove an electron from there. Right. And the electron gain enthalpy will be also more negative as we move along the group. Right. Yes, we have already discussed this. So what happens? Hence, the ionization enthalpy of extreme left element is the least. Right. It is increasing along the period, means in that end, that is the left end, from left to right, the ionization enthalpy is increasing, mean on the extreme left, yes, it will have the least value. And the electron gain enthalpy of the extreme right element will be the highest negative. Right. So this is clear. Now what happens? Because of all these results, This results in high chemical reactivity in extreme ends and lowest in the center. So what did we study? In this periodic table, you can see towards the left, the ionization enthalpy will be very, very less. Yes, as it goes on increasing, that is from the along the period, if we move from left to right, it is keeps on increasing, right? So ionization enthalpy is least in this left region of the periodic table, and towards the right, the electron gain enthalpy is becoming more and more negative, right? So this is clear. So because of this, the chemical reactivity will be more towards the left and towards the right, and it will be very less towards the center. So on the extreme left and right, the chemical reactivity will be more and the chemical reactivity will be less towards the center. Now the maximum chemical reactivity at extreme left is exhibited by the loss of an electron, leading to the formation of cation. We have already discussed this. In the extreme left, we know that the elements will have a tendency to lose electron easily, right? To attain their octet, they can easily lose electrons. So they exhibit high chemical reactivity because they can easily lose electron and form a cation. And extreme right shows by gain of electron forming an anion. And towards the right, if we go, it is easy for them to accept one electron and form an anion. So I hope this is clear. The periodic trends in chemical reactivity. So to summarize this, yes, towards the left and towards the right, the chemical reactivity will be more. Yes, towards the left, they will form cation by losing an electron, and towards the right, the chemical reactivity is more because they have the tendency to accept electron and form a negatively charged ion, that is anion. Yes, I hope it is clear. So now we are going to study about oxides. Right. So what you have to understand is metals give basic oxides and non-metals are acidic in nature. So metals are having basic oxide, they form basic oxides, and non-metals give acidic oxides. Okay. So we know that towards the left of the periodic table, yes, mostly there are metals, right? We have already studied about this in last sessions when we were discussing about metals, non-metals and metalloids. So towards the left of the periodic table, it is mostly metals, and towards the right, it is the non-metals are present, right? Yes. So metals give basic oxides and non-metals give acidic oxide. So this is clear. Now the basic nature of oxides increases down the group. So who forms this basic oxides? That is metals, right? So what did we study about the metallic character? We studied that metallic character increases down the group, right? Down the group, if we go, the metallic character increases because the atom can easily atom can easily lose the electrons, right? Hence the metallic character increases. So if we move down the group, if the metallic character is increasing, that means the basic nature of oxides will also increase, right? So it increases down the group. If basic nature of oxides is increasing down the group, means along the period it will be decreasing. Right? It will be just the opposite. Now moving on to the acidic character of oxide, it decreases down the group. We know that the non-metallic character, what happens to the non-metallic character down the group? Yes, down the group if we move, the non-metallic character will keep on increasing because as the atomic size is increasing, it is difficult to accept one more electron to it. Right. So the tendency of an atom to accept one electron will become less and less when we move down the group. So hence non-metallic character decreases down the group. Hence acidic character of oxides also decrease down the group. So that is clear. Now reactivity of metals increase down the group. We know that down the group as we move, more and more chances are there the electron can easily be lost from the outermost shell. Hence the reactivity of metals will also increase down the group because the atom can easily lose the electrons, right? Now the reactivity of non-metals decreases down the group. For metal, if it is increasing down the group, we know that for non-metals it will be exactly the opposite. So I hope it is clear for you. So by this we come to the end of this chapter. Yes, so I hope what and all we have discussed in this chapter is clear for you. So that's all for today. In the next session, we will be beginning with the next chapter. So thank you.